Let's do 2.4, bounded linear operators. I've tried to advertise functional analysis in a sense as a study of bounded linear operators. Functionals specifically are examples of bounded linear operators. So what we'll do in this section is consider linear operators. We'll put a norm, for now an alleged norm, on these operators and use that to define the idea of boundedness. Operators are mappings from one normed linear space to another. We define the norm of an operator. We don't show it's the norm of an operator just yet. In chapter 6, we'll actually form a linear space out of collections of operators called a dual space of a given space. The normed linear space is X and Y. For such spaces, the set of all linear operators from X to Y is denoted L of X comma Y. We've defined the idea of linear before. With linear spaces, it makes sense to take linear combinations in X and in Y. They're actually just vector spaces. That's all a linear space is. So to have a mapping from X to Y, which is linear, is also well defined. And for T, a linear operator from X to Y, define the operator norm. Okay. So we're defining the operator norm, the norm of T, T being a linear operator, to be the supremum over all vectors in space X such that the norm of X equals 1. So as X ranges over those possible vectors, we're taking the supremum of the norm of T of X. Okay, now let's unwrap what's going on here. Actually, in that single line, there's 3 different norms. There's the operator norm that's being defined. There's the norm here. It's supposed to be clear from context. That's the norm on space capital X, because vector X lives in capital X. Over here, we've got the norm on capital Y, because T is a transformation to X to Y. So when I look at a T of vector X, we're getting a vector that lives in vector space, norm space, Y. So 3 norms. This is going to take some getting used to, more than likely, but 3 norms, and it's clear from context which is which. Nonetheless, I'll probably make a big deal out of it to make sure we're all on the same page when we do stuff like this as to which norm we're actually referring to. So we're defining this quantity, calling it an operator norm. We're not going to establish triangle inequalities and such as that. We're just going to look at some properties of this operator alleged norm at this stage. I'll still refer to it as the operator norm. If the norm of T is finite and is defined as a supremum, so it could well be infinite, but if the norm is finite, then that operator T is said to be bounded. We'll denote the set of all bounded operators in the set of linear operators from X to Y is B of X comma Y, and it's the bounded linear operators that we're ultimately interested in, just as we've looked at some bounded things in the previous section. Okay, so we've got that quantity defined. Let's look at some properties of it. If we take any non-zero vector, lowercase x, in vector space X, then the vector X divided by the norm of X, okay, technically it's 1 over the norm of X as a scalar times vector X. Division's not a defined operation. You don't divide vectors by scalars, you multiply them by scalars, but just read this as vector X multiplied by the scalar 1 over the norm of X. So an arguably imprecise notation there, but that's the meaning of it. So we're not introducing anything new, it's just scalar multiplication. We have divided by the norm of X. Good thing we're dealing with non-zero vectors. But by doing this, we create a unit vector. This is sometimes called normalizing a vector. Simply divide it by its magnitude, its norm, producing a unit vector. You commonly do this when you're only interested in the direction part of the vector. Vectors have, in an informal sense, magnitude and direction. So you often normalize vectors to kind of get to the direction part of it by standardizing the norm of it, making it a unit vector. So if we look at the definition of the norm of this operator above, we could take the norm of t to be the sup of the norm of t of x over all x in the vector space such that the norm of x equals 1, and draw the conclusion that that's greater than or equal to the norm of, for any particular vector x, the norm of t of x times x divided by the norm of x. This is a particular unit vector. So when we take the sup over all unit vectors, then we get something greater than or equal to this particular norm of t of a unit vector. So simply the fact that a simple particular element of a set is less than or equal to the supremum of the set. We bring this up because we got a scalar multiple of t. You can bring that scalar outside the transformation because it's a linear transformation, and you can bring that scalar 1 over the norm of x. You can bring it outside of the norm as an absolute value. Technically, that was a scalar property of norms. So we ultimately end up with the norm of t of x divided by the norm of x. No apologies here for using division symbols. That's just a quotient of two real numbers. Norms are real numbers, and the denominator is not 0 because x is a non-zero vector. Maybe one additional comment. By considering all vectors x of unit 1, if we were to put these vectors in standard position, this was a conversation in sophomore linear algebra, I'd say you're looking at the surface of the unit ball in this normed linear space. And we'll discuss things in the future related to some properties of the unit ball in these normed linear spaces. The unit ball itself is usually all vectors of norm less than or equal to 1. The surface of that is all vectors of norm equal to 1. So what we extract from this little inequality here, we've got the norm of t is greater than or equal to this quotient. We can cross multiply, take the norm of x to the other side of the equation, and that produces the norm of tx is less than or equal to the norm of t times the norm of x. Take this to the other side, we get norm of t of x less than or equal to, reading from right to left, the product of this and the norm of x. Okay, we'll use this fairly often. Let me give this node a name. Let's call it node 2.4.a. So we'll refer back to this occasionally. Straightforward, it really just follows from the definition of supremum. We use norms to measure links, so we can use the operator norm to see if operators preserve links. It turns out, to get a definition of an isometry, a linear operator T mapping normed linear space X to normed linear space Y. That's the meaning inherent in all these here symbols. This operator is called an isometry if the norm of T of X equals the norm of X for all X in the domain space, the normed linear space capital X. So this maps a vector of some particular length to a new vector in the other space that has the same length, same measure, same length, isometry. So it preserves lengths of vectors, is what isometries are. Both of these spaces are normed, that's the setting. For any t, a linear operator from x to y, we can define continuity of t in terms of epsilons and deltas because we can measure distances in x and distances in y. We have metrics on x and y, right? Well, we've got norms on x and y, and norms induce the metric. So we can do pretty much a calculus 1 idea of continuity of these type of operators. So for t, a linear operator from space x to space y, t is said to be continuous at x sub 0 in normed linear space capital X if for all epsilon greater than 0, there exists delta greater than 0 such that, okay, that's very, very calculus 1-ish. And the rest of it's pretty much calculus 1-ish as well. If the norm of x0 minus x is less than delta, then that implies the norm of t of x sub 0 minus t of x is less than epsilon. In other words, for any epsilon, if we make x sub x sufficiently close to x sub 0, the sufficiently is that there exists a delta greater than 0, then function values are within epsilon of each other. So we can make function values as close together as you want by making input values sufficiently close together. All of this being anchored at point x sub 0, continuity at a point. So what you got there is the same thing you have in calculus 1 in talking about continuity of a function or limits of a function, maybe is where you first encounter, but continuity is also usually defined in terms of epsilons and deltas. We could treat these x values that are distance delta from x sub 0, we could treat those as a ball centered at x sub 0 with radius delta. And what we're saying is when we apply t to all such x values, the result is within epsilon of t of x sub 0. In other words, apply t to all those x values sufficiently close to x sub 0, and you'll get something that's within epsilon of t of x sub 0. Here it is written in terms of the image of balls of radius delta versus balls of radius epsilon. These being, let's see, centered at x sub 0. So this would be a little subset of normed linear space x. These being centered at t of x sub 0 would be subsets of normed linear space y. So the balls are based on metrics in different spaces or norms in different spaces, as far as we know. All right. T is said to be uniformly continuous on x. So that's glad I got these side by side. Let's go through and compare this and see exactly how it differs from the definition of continuity. Uniform continuity versus continuity says, for all epsilon greater than 0, there exists a delta greater than 0, such that, so far it's the same, x1 minus x2 in norm less than delta implies t of x1 minus t of x2 less than epsilon for all, that's the uniform part, for all x1 and x2 in set x. And this could also be defined on a subset of x. That's the parenthetic comments. So we could have uniform continuity on a subset of set x. But now the difference between uniform continuity and continuity, the continuity up here at point x sub 0 played a role, both in input values and output values. Uniform continuity, x1 and x2 could be anything for all x1 and x2 in normed linear space x, provided they're within delta of each other in the norm sense. So you might say uniform continuity tells us no matter which x1 and x2 I choose, provided they're sufficiently close together, we'll get their output values to be within epsilon of each other. We start with epsilon, then we can pick a delta that'll work uniformly throughout that space for this implication to hold. That's the difference between uniform continuity and continuity at a point, as you see in senior level analysis. Okay, we got, I think we got 2 or 3 theorems in this section. These aren't terribly involved. This is a claim of equivalence. The proofs aren't complicated. This result's a little bit surprising, possibly. Just read it off of the Beamer files. It says for T, a linear operator from normed linear space X to normed linear space Y, the following are equivalent. T is uniformly continuous on X, is equivalent to T is continuous at some point x in that space. And those are equivalent to the fact that t is bounded, a bounded operator. So, well, first off, uniform continuity implies pointwise continuity. That's trivial, that's unsurprising. The fact that we get these implications to go both ways, that's surprising. The fact if we have a linear operator continuous at a single point, that implies uniform continuity, that's a touch surprising. You certainly don't see functions behave like this in general. Must have something to do with the linearity of the function. All right, so let's go through proof. First, 1 implies 2. That's trivial. 2 implies 3. Let's go through proof of that. So suppose t is continuous at point x. So we're fixing this vector x for this argument. You know, for all epsilon greater than 0, there exists a delta greater than 0, definition of continuity. Let's take epsilon to equal 1. We're trying to get that t is bounded. So I don't need necessarily an elegant bound, I just need a bound. Take epsilon equal to 1, then knowing t is continuous at point x, you know there exists a delta greater than 0, such that if we'll take a ball centered at x of radius 2 delta for reasons to be explained here shortly, we apply the transformation to that, you'll get a subset of the ball centered at t of x with radius 1. So this is simply saying if we take input values sufficiently close to x, sufficiently close for making 2 delta here, then we'll get function values this close within a distance of 1 of t of x. Input values sufficiently close to x, output values as close as desired, and there's what's desired this time, to t of x. All right, so we're trying to show t is a bounded linear operator that was based on unit vectors. So let z be a unit vector in norm linear space capital X. Norm of z equals 1, it's a unit vector. Then consider x plus delta z. All right, how far is delta z from x? Well, z is a unit vector, and the distance here is at most delta itself. Well, if you choose points within delta of x, then I might not get something in the ball of center x and radius delta. We could have some problems on the boundary. But I certainly get something z, x plus delta z is within a distance delta of x. So it actually lies in the closed ball of center x and radius delta. But we've got overkill here. This is why we introduce the 2 delta. We do get x plus delta z, an element of this ball. All right, so that's why the 2 delta was introduced upstairs. So we know, having chosen x plus delta z to be in a ball of center x and radius 2 delta, if we apply the transformation to that vector, then we'll get something in this ball centered at t of x with radius 1. We're going to mention that down here. So apply transformation t to x plus delta z. T is a linear transformation. So use the linearity property. That equals t of x plus delta t of z. Preserves linear transformations, and scalars come outside of transformations. So we get this. And as we just observed, since x plus delta z is in this ball, then the image of it is in this ball. The image is t of x plus delta z. You know, that lies here. All right. So we can conclude here we've got something delta t of z. This little thing here gives us, in a sense, displacement from t of x. Well, the displacement from t of x to lie in this ball is at most 1 if you want some geometry, maybe it's a little cleaner to do it algebraically. Delta T of z, if we consider this, delta T of z equals T of x plus delta z minus T of x. Simply take this to the other side of this little equation and put norms on it. So we get a norm like this. We then have this, the norm of this difference to be less than 1, as we just discussed. I know delta times T of z, delta times T of z is within a distance of 1 of T of x. So we get this difference in norm to be less than 1. And the conclusion to draw from that is delta norm T of z less than 1. Divide both sides by delta, get norm of T of z is less than 1 over delta. Norm of T of z is less than 1 over delta. So playing around with the epsilons and deltas, a particular epsilon, knowing continuity says for all epsilon, we can find deltas. So we can pick a particular epsilon. We were given continuity, and we're trying to show boundedness. So what we have is T of z is less than 1 over delta, where z was an arbitrary unit vector. Well, we define the norm of T of z to be the supremum of all of these things, where z was a unit vector. Well, if all of these things are bounded by 1 over delta, then taking a supremum over all such things, all such z, a unit vector, we'll get the supremum to be bounded by 1 over delta as well. We'll pick up an equality when we go to the supremum. So we get a less than or equal to in that case. And so the bound on the norm of T is 1 over delta, and T is a bounded linear operator. This might look a little odd, but think, yeah, epsilon, we could have made epsilon smaller and done the same type of thing just by choosing a specific epsilon value. But kind of the crude idea is for given epsilons, I mean, the deltas might be big here. We're just looking for an upper bound. Sorry, the delta should be little. So if we're given epsilon, if epsilon's little, I expect delta to be little as well in some crude sense. And we're getting 1 over delta as a bound. So is this an efficient bound? I don't know. It could be quite big. If delta is little, then 1 over delta could be quite large, just to put some intuition on it. But we've got this boundedness on the norm, and so we have a bounded linear operator. So 1 implies 2, 2 implies 3. Let's show 3 implies 1, and that'll wrap a little implication around in a cycle. So we're going to assume T is bounded, say the norm of T equals capital K. Let epsilon be greater than 0, be arbitrary, and take delta to be epsilon over K. Delta is based on epsilon and based on the norm of T. Then for any xy in norm linear space X, provided the norm of y minus x is less than delta, so they're within delta of each other, we'll get the function values are within epsilon of each other. And that's uniform continuity. So we took any x and y within distance delta of each other, and we will calculate and show the function values, the output values in norm are less than epsilon. That's the definition of uniform continuity. Okay, this differs from what we did when we assumed part 2. We had a specific point x. Here, x and y could be anything for any x and y sufficiently close together. All right, let's show our alleged sufficiency is actually correct. Well, the norm of T of x minus T of y, that's less than or equal to the norm of T times the norm of y minus x. That was that note 2.2.a that we mentioned earlier. The norm of T, we said, assume that as K. Y minus X, we just took to be within delta of each other. So we'll know that norm is less than delta. We had chosen delta to be epsilon over K. Substitute that in, the K's cancel, there's the epsilon, and that's exactly what we needed to show. So that implies T is uniformly continuous, and we've got the equality of those 3 properties. So, really, the surprising one is piecing these together. Continuity at a point implies uniform continuity. for linear operators. Continuity to point implies boundedness. I mean, that's pretty weird too, if you think of it in terms of just ordinary functions of a real variable. Of course, there's unbounded continuous functions. But the fact that continuity to point implies uniform continuity, that I take as a little bit surprising. It's got to have something to do with the linearity. All right, so back to the notes and an example 2.7 from the book. Consider the set of bounded functions on set S, B of S, with a suit norm. We introduced this in the previous section when we were looking at, was it bounded? What were we looking at there? We saw this in the previous section, 2.3. When we looked at bounded functions on this set, we put a norm on them. We actually showed this thing was a normed linear space under the suit norm. All right, so normed linear space, the norm on that space was a suit norm. Take yourself G, an element of this, so that means G is a function defined on set S, and G is bounded with respect to the suit norm. Also recall, maybe somewhere in here, these functions G, they gave out real numbers, right? They took in elements of the set and they gave out real numbers. That's how we define this thing. That's how we dealt with the boundedness in the suprema. For such a G, define a linear operator M sub G. Okay, so going to be lots of different norms here. There's going to be a norm on the linear space. There's going to be a operator norm as well. So define the linear operator M sub G to map this normed linear space into itself as follows. Take an F in B of S, a function defined on set capital S, which is bounded with respect to the suit norm. The operator M sub G takes such a function and maps it to the function G of S times F of S. M sub G is called the multiplication operator. That's why they denote it M sub G, M for multiplication, sub G, because what's the function multiplied by? What is F multiplied by? Function G. So you're simply taking any function F in the B of S, and for this chosen function G, you're multiplying G of S times F of S and producing a new function. We claim the norm of M sub G, the operator norm of M sub G, equals the norm of G. Okay, different things, different norms. Operator norm here, norm on space B of S here because G lives in B of S. Well, if G lives in B of S, then you talk about the norm of G using the norm on that linear space B of S. It was a suit norm. Okay, but we're claiming equality here, but these are different things, G and M sub G. They live in different places, and these are therefore different norms. One's an operator norm, one's a norm on a normed linear space. All right, so take F to be an element of the B of S, the bounded functions on set S, such that F has norm 1. Okay, which norm is that? Well, F comes from this, so it would be the norm on the B of S space, and that was, as we mentioned up here, B of S has the suit norm on it. That's how we define this thing. So this is a norm on B of S. It was a suit norm, by the way. So F is a unit vector. Let's take that function F and apply the multiplication operator M sub G to it, pointwise first. So if we take M sub G of F, apply that to element S of the set, that by the very definition up here gives us G of S times F of S. Okay, remember, F and G just take us into the real numbers. So absolute value is a thing to talk about there. Absolute value of the product is the product of the absolute values. This is true, just a little parenthetic comment, an unelegant place to put it, but this little equality, this holds for all S lowercase s, and set s, simply an absolute value property. What's the norm of G? Sup norm, because we're taking G from this B of S space. Well, the sup norm is greater than or equal to the absolute value of G of S for any S in set capital S, because a sup norm is defined as the supremum of all of these as S ranges over set capital S. So the norm of G is greater than or equal to one of these specific values. Similarly, the norm of F is greater than or equal to one of these specific values. So we've got a bound on this of norm of G times norm of F. But remember, we chose a norm of F to be 1. We chose F as a unit vector. So this simply equals the norm of G. All right, here's what we're trying to show. We've got something is less than or equal to the norm of G. That something, it isn't this. It's related to it, but it's not this. So we're going to show an inequality in 2 different directions. Strictly speaking, we ain't even halfway yet. But this isn't terribly long. All right, so we've got this inequality established. Absolute value of m sub g of f evaluated at s is less than or equal to the norm of G. Let's take a supremum in this inequality over all S. Take a sup over all S. That shows us that supremum over all S of these things, that's giving us the norm of this thing highlighted, m sub g of f. Right? You've got a thing evaluated at S. By the way, that thing lives in B of S. Right? We've seen worse things in the definition of sup norm. We had 3 norms there. Here we've got 2 norms. We've got the operator norm and we've got the norm on B of S. Yeah, previously we were mapping from one normed linear space to another. At least this time we're mapping from one normed linear space into itself. So we only got 2 norms here. But m sub g of f, hey, that is an element of B of S. So this highlighted thing here is an element of B of S. So if we want to talk about the norm of it, it's a sup norm. So we simply take the absolute value of that thing evaluated at S and take a supremum over all S in set S. Like it says, take a supremum over all S in set S. You take a sup of this collection of real numbers as S ranges over that set capital S. They're always bounded above by the norm of G. So when you take the supremum, you get something bounded above by the norm of G. Also, when you take a supremum, you get the norm of the highlighted thing. That is, you get the norm of m sub g of f. So now we're halfway, pretty much. We've got here, this is a norm in B of G, so we still have a little ways to go. And this is also the norm in B of G. We still haven't reached the operator norm, right? It's coming up in the next line. But this is a norm of a specific element of B of S. We need to take that and transform it into operator norm. Well, we chose F to be, chose F to be a vector of norm 1. How did you define the operator norm? By taking a supremum, again, this time, over all unit vectors. So we'll take a supremum over all unit vectors F in this inequality, and that'll allow us to conclude that the sup of all of these, which is by definition the operator norm of m sub g, that's bounded above by the norm of G as well. Let's go back and look at operator norm one more time. Operator norm was defined as, yeah, here it is. No, there it isn't. There it is. Operator norm of an operator is defined as the supremum of the norm of that operator times a unit vector, that operator acting on a unit vector, x. And the sup is done over all of those unit vectors, all x in the input space, the domain space of the operator. That's exactly what we have. We've got m sub g, the operator, that's the t in what we had before, and it's acting on a unit vector. That's the x we had before. In the definition, we had tx. Here we've got m sub gf. Sometimes I put the parentheses in, sometimes not. So between me and the text, we're a little inconsistent with that. But we wanted a operator norm, take a sup over all unit vectors x. I mean all unit vectors f here. And we just showed if f is any unit vector, then this quantity is bounded by norm of g. We set all this up with f as a unit vector. Take the sup, this becomes the operator norm of m sub g, and take a sup. We've got this bound on each of the terms. You've got that same bound on the suprema. Okay, so the operator norm is less than or equal to the norm of g. Now we're totally legitimately halfway. We need to reverse that. We're going to reverse that by finding a particular vector, a function, bounded function on set S, to which to apply m sub g and show that we actually attain this bound here. For any element S in set S, consider the characteristic function chi sub S of x to be 1 if x equals S and 0 otherwise. Probably you encountered characteristic functions in possibly in senior level analysis, certainly in graduate real analysis 1. Characteristic functions come up on sets. Here we've got a characteristic function that's 1 just at a single point. So there's a function that's 0 everywhere except at x, where it takes on, except at s, where it takes on the value 1. That's an element of B of S, ain't it? Yeah, it's a bounded function. It's defined on set S. 0 everywhere at one point, and at that one point, it's 1. So it's bounded. It's bounded by 1. Quick comment: the textbook denotes this as delta sub S. I prefer the characteristic function notation. It's just notation, though. So we get the following. All right, so let's look at G of S. We can write G of S as the operator, m sub g, acting on this characteristic function. Because what's this going to do? It's going to take that characteristic function and it's going to multiply it by G of S. Well, if we take the characteristic function here, multiply it by G of S, it's totally going to disappear except at fixed point, lowercase s itself. So we're picking out an individual value of s, in this case, the s given by the characteristic function, and we can write G of S as this operator applied to that characteristic function. You'll multiply, you'll lose everything, you'll pick up G of S as the function at a single point. So definition of multiplication operator is what establishes this equality. Now we've got operator applied to a function at a single point. That note we had up above allows us to draw the conclusion this will be less than or equal to the product of the respective norms, the norm of the operator times the norm of the input function, the norm of the characteristic function. Okay, how y'all doing out there? What's the norm of the characteristic function? Well, that depends. Where is it? It's in B of S. Okay, that's a norm linear space and has the sup norm on it. So asking what's the norm of that function vector is the same as asking what's the supremum of these function values, these function values? Well, it's 1. The biggest one is 1, and all the others are 0. So the soup is 1. So the norm of that function is 1. And we get the simply then the norm, the operator norm of the multiplication operator, m sub g. All right, so for any s, we're able to pick a corresponding characteristic function and show the absolute value of g of s as less than or equal to the norm, the operator norm of m sub g. So if we take a supremum over all s in capital S, lots of supremum taken, yeah, that's because everything is sup norms in this example. B of S has a sup norm on it. And the operator norm is defined in terms of supremum as well. So that's why all this repeated stuff with take a supremum, take a supremum, take a supremum. So take another supremum over all S and set S. This quantity that will produce the norm of G. You just saw for any particular S, we get that absolute value bounded above by the operator norm m sub G. Take the sup, it'll have the same bound. In other words, the norm of G is less than or equal to the norm of m sub G, but they're different norms. We had upstairs the reverse of that inequality, leading us to a conclusion of equality. And that's what we were trying to show in this example. I might recommend rewinding and watching this again, read it in the book. It's not that complicated, but in the beginning, I think it's pretty tough to get a handle on all the little moving parts. There's norms all over the place. You're always taking suprema. Sometimes we're in this space, sometimes we're in that space. Sometimes we got vectors, sometimes we got operators, and the operators and the vectors have different norms, but the operator norm is defined in terms of vector norms. So lots of moving parts. Let's compose linear operators. If T is a linear operator mapping normed linear space X to normed linear space Y, and S is a linear operator mapping normed linear space Y into normed linear space Z, if these are bounded linear operators, then the composition of S and T is defined as ST mapping X into Z, where it's simply the composition S composed with T of a vector X, that is ST of X, this is notational stuff here, is computed as S of T of X. It's a composition. Of course, you need the output from T, which lives here, to be input for S. The range of T needs to be in the domain of S. So that's why these are the same spaces. These are both Y, the output of the T's, the codomain of Y is the domain of S. Is a proper way to say it. So we can compose bounded linear operators. I wonder how their norms behave. Compositions of continuous functions are continuous. So if S and T are both continuous, then their composition is continuous. Standard stuff you show in senior level analysis, might even pop up in at least a statement of it in Calculus 1. Compositions of continuous functions are continuous. Hey, Theorem 2.6 tells you then, so if S and T are both continuous, then they're both bounded. Theorem 2.6 implies that. The composition is continuous by some standard analysis stuff. Theorem 2.6 tells you that must be bounded too. So if S and T are both bounded, then their composition is also bounded. Quick argument just based on Theorem 2.6. Really using the fact that we know a lot of stuff about continuity coming into this class. So continuity arguments allow us to make boundedness conclusions. By the way, also let you make uniform continuity conclusions as well. So we've got that this composition, the book commonly denotes it, they just put them side by side, but it's understood composition is the operation between those two. We know it's bounded. What is its bound? Well, the following result gives a bound on the norm of ST in terms of the norm of S and the norm of T. And it's probably not terribly surprising that the bound on the norm of the composition, upper bound, is the product of the norms, product of the norm of S and the norm of T. Here they're claiming we're taking S and T to be bounded linear operators. They actually make two claims. They're claiming that the composition is linear and that the composition has a norm bounded above by this quantity. So let's go through that. Okay, two claims. Actually, it fits on one slide, so let's just look at it. Claim of linearity. All right, take your two vectors in input space X, and S composed with T maps X, that's the domain of the composition, ST, takes X and maps it to Z. But anyhow, the input is still normed linear space, capital X. So take two vectors from capital X and take two scalars, taking our scalars to be real. I think mostly from here on out, we're taking the scalars to be real. We'll be clear on where the scalars come from. In fact, they could be from any field as far as this is concerned, in terms of the linearity part at least. We'll take ST and apply it to the linear combination. That means take S of T applied to the linear combination. Well, T is linear. That's what this L right here means. So T of the linear combination is the linear combination of the T's, as I say it. Calculation-wise, we get this kind of thing. Not distribution, linearity property, definition of linear. Now we've got a linear combination of vectors again, and we're applying S to it. S is linear as well. So when we apply S to the linear combination, you get the linear combination of the S's. The S's and the T's get together and you've got the little composition again. So we've taken this and applied it to a linear combination and got a linear combination involving this, the ST. That is, ST, S composed with T, is also linear. So there's the linearity. How's about the norm stuff? Take yourself a unit vector from X. Remember, the norm of operator ST is defined to be a supremum over all such X. So take a particular X, then ST of X. We've got S of T of X, view it that way. The note we called attention to said this is less than or equal to the norm of S times the norm of the vector. The vector is Tx, first off. So we're using note 2.4.a really on operator S and vector T of X. Do it again. Now apply note 2.4.a to T of X, norm T and vector X, and that produces a norm of T and a norm of X, operator norm and vector norm. Oh, but wait, we took X to be a unit vector, so we can drop that. And we've got the norm of S of T of X is less than or equal to this. It's not exactly the end of it. We still need to take a supremum over all such X. Hey, all of these vectors are in norm bounded by this constant. So when you take the supremum, it's also bound by this constant and produces this. And that's where the conclusion comes from, as claimed. Okay, let's see, nothing else from the notes. So that takes care of this section. There's a handful of properties on bounded linear operators. What's to follow is looking at some more properties of operators, properties of normed linear spaces. I think completeness is next. We want to talk limits, and we have to have completeness if we're going to deal with limits in any of these settings. Limits only make sense in a complete space. You dealt with completeness in the real numbers setting, no doubt. We're trying to take that idea of completeness into this new setting of normed linear spaces. So I will see you in the next section shortly. Have a nice day.